in this morning, in today's PRISM series number 3 webinar, we are very glad to invite 4 distinguished Japanese colleagues to share with us about their experiences on the space instrumentation. Especially, we are in this series talk, we will cover about the measurement on about magnetic field and the electric fields, and the optical observations, and the plasma particles measurements, and also with the ionospheric plasma density and the electron measurements. So it is very broad topics can be covered today. In the first talk, we are very glad to invite the Professor Matsuoka from Kyoto University. She is the expert on about the in situ measurement for the magnetic and electric field in a lot of excellent and outstanding space missions. So it is very glad to invite Professor Matsuoka to give this talk today. So Professor Matsuoka.
Thank you very much. And thank you very much for inviting me today. And I'm Ayako Matsuoka in Kyoto University. And today I want to talk about the in-situ measurement of the magnetic and electric fields in the space. But my talk is mainly on the magnetic field, the measurement in the space. But of course, I will talk a little bit about the electric field measurement also. And at first, I start with the magnetic and electric field in the space. It is a very the rough the overview of the nature of the magnetic and electric field in the space. There are some the sources of the magnetic field in the space, and they are categorized. They can be categorized in 4 origins. The first one is the so-called dynamo process is working in the interior of the sun and the planets, and it generates the magnetic field in the area around the sun and the planet, and also for some the moon satellites, and the rocks on the surface of the planet, and sometimes the moon satellites are magnetized by the magnetic field generated by the dynamo process, and that is the second origin. And the third one is the electric currents flowing in the space. Do you look at the pointer on the screen? Is it okay? Okay, and this figure shows the so-called L-state experiment. The electric current flowing in the space generates the magnetic field, and the so-called L-state experiment, he flows the current on this line, and found that the compass needle moves corresponding to the on and off of the current. And the fourth one is the electromagnetic variation. And I think that you know that the electromagnetic waves are accompanied by the varying magnetic field and electric field. And our most familiar the magnetic field is the geomagnetic field. And this figure shows the distribution of the magnetic field, the intensity on the surface of the Earth. And we can see that the magnetic field is most intense in the North and the South Pole region. And the magnetic field at the equatorial area, equatorial region is about half of the that of the pole region. It is because the geomagnetic field has the dipole the configuration, and it has some intense in the pole regions. But if we look at some area the more the distant from the Earth, the magnetic field the configuration is a little bit different. Magnetic field is compressed in the day side and extended elongated in the night side. It is the modification of the magnetic field configuration around the Earth is generated by the solar wind. We usually call the area where the geomagnetic field affects is the magnetosphere. This is the magnetosphere, and the boundaries or the size of the magnetosphere is determined by the balance between the solar wind dynamics pressure and the magnetospheric pressure. So the magnetic field in the day side is compressed by the pressure from the solar wind. So the magnetopoles it is the boundary of the magnetosphere is its position is determined by the magnetic field intensity generated by the Earth and the dynamic pressure of the solar wind. And in the other hand, the magnetic field configuration in the magnetosphere is modified by the current flowing at the magnetopoles. Here is the magnetopoles. And this figure shows more in detail about the current flowing on the magnetopoles. The magnetopoles current flowing at the magnetopoles is direct from dusk to dawn in the high latitude regions here and here, but that current flow from dawn to dusk on the day side here, and there are different type of the current system in the magnet tail. It flows from dawn to dusk in the center of the night side magnetosphere. It is called the magnet tail current. And so the dipole configuration in the vicinity of the Earth are stretched towards the night side by the electric current at the far distances. So the current as a system has the 3D structure, and this figure shows the 3D structure of the magnetospheric currents. The real magnetospheric current system is a little bit complicated, but it has the magnetopole current here, and the tail current here, and there is some the current connected between the magnetosphere and the ionosphere. And these currents generate the additional magnetic field in the magnetosphere. And I move to some of the topics about the electric field in the magnetosphere. And I talk a little bit about the charged particle motion in the electromagnetic fields. In the uniform magnetic field, both the proton and electron make the cyclotron motion like this. But a magnetic field does not magnetic field does not give energy to the proton and the electron because the magnetic field force works perpendicular to the proton and electron motions. But in the existence of the electric field, both the positive ions and the electrons are accelerated or decelerated by the electric field. For example, the electric field direct to this direction. The positive ion is accelerated in the same direction, and the electrons are accelerated in the opposite direction. So the electric field gives the energy to these the charged particles. So the electric field is very closely related with the auroral phenomena. This figure shows the cartoon of the electron, the acceleration in the auroral region. This is the surface of the Earth, and this is the Arctic Circle. And when the electric field is there is some electric field around the magnetic field and the field line, and when the electric field is upward, the electrons are accelerated to the downward, and it generates the auroral luminous, illuminate some aurora. But in some cases, the electric field direct to the downward, and in this case, the electrons are accelerated to the upward, and below this region, the aurora did not aurora does not appear, and there is no auroral luminosity, and this the area is sometimes called the black aurora, and so the electric field plays a very important role in the auroral phenomena. So I go to the planetary the magnetism of the planet. Of course, we have there are several other planets in the solar system, and the most intense planet in the solar system is the Jupiter, and the Saturn and the Uranus and the Neptune. Those are some of the outer planets have the more intense magnetic moment than the Earth. And on the other hand, the inner planets have the less intense magnetic moment, or they do not have the magnetic moment. For example, the Mercury has the less intense magnetic moment than the Earth. And Venus and Mars does not have the planetary magnetic moment, but the Mars is said Mars used to have the planetary magnetic moment in the ancient the Mars era, but currently it does not have the very global magnetic moment positioned at the center of the Mars, and there are some the crustal magnetic field that is some of the magnetized rocks on the surface of the Mars. So the magnetic field moment is different depending on the planets And of course, the solar wind pressure differ depending on the location of the planet. So this the figure shows some of the plot of the magnetic field strength at the planetary surface and the magnetic field strength at the magnetic poles, and also the magnetic field strength in the solar wind. And we can see that the magnetic field strength at the surface is most intense for the Jupiter, and that for the Saturn is very similar to the Earth. But of course, Saturn is a very big planet, so the magnetic moment of the planet is much bigger than that of the Earth. And the difference between the magnetic field strength at the planetary surface and the magnetic field strength at the magnet pole. The magnetic field strength at the magnet pole is determined by the solar wind pressure at the planetary position, as I talked at the beginning of my talk. And in the case of the Jupiter, there is a very big difference between this magnetic field strength and this magnetic field strength, and it indicates that the Jupiter has a very big magnetosphere around the Jupiter, and the Earth and the Saturn also have the very big magnetosphere. On the other hand, the Mercury has the magnetic field moment of the planetary magnetic field magnetic moment, but because the magnetic field strength at the planetary surface is very, very close to the magnetic field strength at the magnet poles, and it means that the Mercury has a very small magnetosphere. And okay, so I want to talk a little bit about the magnetic field observation of the Mercury. Mercury is a very difficult planet to explore, and I will talk about the reason in the next slide. The Mercury was firstly explored by the Mariner 10 flyby. It is the Mariner 10 did not orbit around the Mercury, just made the flyby 3 times flybys. This figure shows the magnetic field, the observation by the Mariner 10 by the first flyby. The Mariner 10 passed in the night side of the Mercury, and it found the tail-like. Tail-like is the night the magnetic field pointing to the night side. In the night side of the Mercury, and it was very controversial if the Mercury has the planetary magnetic field or not. And some people some people discussed that these magnetic fields are caused by the deformation of the solar wind magnetic field. But at the third flyby, the Mariner 10 passed the pole region of the Mercury. It is the view from the day side, and it shows that the Mariner 10 passed the pole region of the Mercury, and it shows the very clear dipole configuration of the magnetic field, and it was finally understood that the Mercury has the planetary magnetic field, and it has the magnetosphere although it is very small. So the Mariner 10 flyby was occurred in 1974, and Mercury was the very last planet explored by the spacecraft. Why so difficult to explore the Mercury? It is because the Mercury is very close to the Sun, as you know. The distance from the Sun is from 0.3 to 0.47 AU, and so the radiation from the Sun is 10 times intense than that of the Earth. So that it makes the spacecraft the high temperature, and the spacecraft have to be tolerate to the very severe radiation environment. So it makes very difficult to explore Mercury. So the first spacecraft orbiting around the Mercury is the Messenger launched by NASA, United States. It was launched in 24 and observed the Mercury in and after 2011. And this is the figure of the Messenger spacecraft. And because, as I said, it should be tolerated for the very intense radiation from the Sun. It has the sunshade here, so it always points to this the direction. Always point to the Sun to protect the heat and the radiation. Protect the spacecraft from the heat and radiation from the Sun. And this is the boom for the magnetometer, and they have the sensor here, a magnetometer sensor here. And I will talk about the boom for the magnetometer at the end of my talk. And it has the Messenger has some orbit like this, and it is very the apogee is here, not apogee. Apogee is here, and the perigee is here, and it is because sorry the perigee, the Messenger has the perigee in the northern hemisphere, and always apart from the Mercury in the southern hemisphere. So of course to measure the planetary magnetic field, the spacecraft should approach to the planet. So the Messenger made a very good measurement of the Mercury magnetic field, but the magnetic field structure in the southern hemisphere of the Mercury has not well examined because due to the orbital configuration. So the second orbital the spacecraft orbiting around the Mercury is the BPColombo. That is launched in 2018, the October in 2018, and now the BPColombo is traveling to the Mercury, and we are now expecting that the arrival at the Mercury in 2025 December. So that we have to wait another 5 years for to have the start the observation as the Mercury. And the BPColombo consists of the two spacecraft. One is the MMO, and it is called MIO in Japan, and it is built by the JAXA in Japan. And another one is the MPO spacecraft that is built by the ESA, European Space Agency, and launched by the Ariane rocket of the ESA. And the MMO and MPO always orbit in the same plane, but the orbit is different. The MPO has the orbit closer to the Mercury, and this is the polar orbit. The perigee is 480 kilometers, and the apogee is at the 1500 kilometers. And on the other hand, MMO, built by JAXA in Japan, has the more different orbit, and it has the apogee at about 10,000 kilometers to observe the more the bigger area in the magnetosphere. The MMO is the Mercury magnetospheric orbiter, and it is optimized. This spacecraft is optimized to survey the magnetosphere of the Mercury. So I want to introduce some of the magnetometers installed on the MMO. We have the two sets of the magnetometers. Both are the three-axial magnetometers, and this is the boom for the magnetometer sensors. And this is the sensors are covered by this the heat shield, so that we cannot look at the sensor from the outside. But inside, we have the two sensors here at the tip of the boom, and here at the middle of the boom. This is called the outside sensor, and this is called the inside sensor. And this sensor is built by the European groups, led by the Austrian the space agency, and this the sensor is this magnetometer. The inside inboard magnetometer is built by a Japanese group. So I move to some of the instrumentation, magnetic field measurement in the space. And we usually use the Fluxgate Magnetometer for the DC, from the DC to the 100 Hz magnetic field measurement. It is the very most commonly used the magnetometer for the spacecraft missions. And it consists of the sensor part and the electronics part. And the electronics part has the driver to excite the magnetic field in the core of the sensor, and some amplifier to process the pickup signal from the sensor, and the feedback part to for the very good linearity of the measurement. But I do not go into the detail of the circuit today. There are some necessary factors for the accurate magnetic field measurement. The first one is, of course, the good performance. We need the good performance magnetometer for the very accurate magnetic field measurement. And the second one is we made the calibration to obtain the parameters to calibrate the data to convert into the physical values. And the third one is the magnetic cleanliness of the spacecraft. The spacecraft generally cause the artificial magnetic noise, and it is often the program for the accurate measurement of the natural magnetic field. So that we make the many efforts to make the magnetic cleanliness of the spacecraft. And in many cases, we need the boom to separate the magnetometer sensor from the spacecraft, even when we make the magnetic cleanliness effort of the spacecraft. So this figure shows the magnetometer development we made in Japan. And of course, we made the magnetic field measurement by the spacecraft before Nozomi. But in this the figure, I start with the Nozomi. That is the Mars mission. And unfortunately, we could not succeed to insert this spacecraft in the orbit around the Mars, so that we could not have some data around the Mars. But that was the first the spacecraft to explore the other planet in Japan. And we installed the 16-bit analog type magnetometer for this Nozomi. And this number of the bit indicates the resolution of the magnetic field. And so that it is a very good indicator to show the magnetic field and the resolution. And in 27, we launched the Kaguya. That is a lunar mission. That was a very successful mission, and we used the 16-bit analog type magnetometer for this mission. And after that, we made a few new development of the magnetometer. The one is the digital type magnetometer. And I installed this digital type magnetometer for the sounding rocket experiment for several times. And another development we made is for the more accurate magnetic field, the magnetometer with the higher resolution. For the ERG, that is Arase, we launched in 2016, and we made some new development, and we installed the 20-bit analog type magnetometer. And we made very similar, we used the very similar design a magnetometer for the BPColombo MMO MIO. That is a Mercury mission. I already talked. That is again the 20-bit analog type magnetometer. For this development, we usually you built the several test board and made the steps of the magnetometer development. In the case of the BPColombo MMO, for the magnetometer for the BPColombo MMO, we made the breadboard model twice. This is the first one and the second one. And the breadboard model is some test board, test circuit to test some special technique we want to develop. And based on the test result of this breadboard model, we built the engineering model that is almost equivalent to the final flight model, and we built the final the flight model. That is now, this board is now traveling to the Mercury now. And of course, we make the calibration of these models, these models. And we in Japan, we make this calibration activities in the test facility, magnetic field test facility, located in the Tsukuba, the space center of JAXA. That is the very big coil system. The diameter of the coil is 15 meters to cancel the geomagnetic field and create generate the area where the magnetic field is almost zero. We need the big coil system to have the uniform zero field the area. In the case of the Tsukuba the facility, the uniformity of the field is about the 80 centimeter, 800 meter diameter sphere, and inside this sphere, the magnetic field the uniformity is within the 0.5 nanotesla. And of course, because the geomagnetic field varies a little bit, so we need to make some kind of the control of this cancellation magnetic field for the stability of the field. At the stability of the field at the center of this facility is 0.5 nanotesla, and the stability is with the frequency of the 10 hertz, and 10 hertz, and the stability is within the 0.5 nanotesla. And we make the calibration test inside this test facility. And the next topic is the magnetic cleanliness of the spacecraft. And as I said, the magnetic field generates the stray field and magnetic noise, and it is always the program to make the very good measurement of the magnetic field in the space. There are some reasons of the magnetic noises. One is the magnetized magnetic the materials. For example, iron, nickel, and stainless steel. And we usually we must replace these materials with the non-magnetic materials, for example, aluminum or the copper. The second one is some instruments have the permanent magnet. And of course, we cannot remove this as an instrument. We need sometimes needs some instrument with a permanent magnet, of course. So in these cases, we sometimes use some additional magnet to cancel the magnetic field generated by instrument, or sometimes we shield the magnetic field of these instruments. And the third one is the electric current in the surface of the spacecraft generates the magnetic field, and it makes the noise. we usually make some effort to reduce the loop area of these electric current loop. And we make the experiment to measure the magnetic noise from the instrument on board the spacecraft. We have the different type of the magnetic field experiment facility, and we have the magnetic shielding room. Sorry, this is the one, so that we can. It is the diameter is about 5 meters. We have this kind of the magnetic shielding room in Sagamihara in JAXA. And for example, the MMO Mercury orbiter can enter into this shielding room, and we measure the magnetic field generated by this spacecraft inside this shielding room. And this is a result of the magnetic field generated by the MMO spacecraft at the 2.4 meter distance from the spacecraft center. It is about just less than 10 nanotesla at the 2.4 meter from the spacecraft center. Sorry that it is a very complicated figure, but the distance from the center is the intensity of the magnetic field at the different positions around the spacecraft. Sorry, maybe I have to hurry. And sometimes we, of course, we have we need the boom to separate the sensor from the spacecraft, because even when we make every effort to reduce the noise from the spacecraft, if we put the magnetometer sensor on the surface of the spacecraft, it is very difficult to measure the magnetic field as a very weak magnetic field in the space. So that we usually use some deployment booms to separate the magnetic field magnetometer sensor from the spacecraft. So I move to the electric field measurement in the space. This is the one example of the electric we need again some booms for the electric field measurement. In the case of the cluster, they have the 50-meter wire booms to measure the electric field. These are the very thin boom is here, and these are some antenna or the wire boom to measure the electric field. And we also have these are similar the antenna, electric antenna for the RC ERG here. But the length is shorter. It is 15 meter. Of course, if we have the longer boom or the longer antenna, we can make the better the measurement of the electric field. And I want to explain the single probe and double probe measurement. This is some figure shows the spacecraft at the center, and when it deploys the one pair of the electric the probe in this direction and in this direction, and we can measure the potential difference between the tip of this antenna and the spacecraft, something like this. And we can measure the potential in reference to the spacecraft potential. And we can measure the potential of this tip of the boom in reference to this spacecraft. And the difference between the potential between here and here is a single probe, and the the potential difference between here and here is a double probe. And I'll skip this figure. And so as I said that we measure the potential difference and here and here and here and here, and we can obtain the potential difference between here and here. So if there is some offset in the of the offset of the potential from the natural plasma potential, we can measure the real potential difference by the double probe as a mode, because this offset is different between for the tip of the probe and the spacecraft. Maybe usually the offset is bigger for the spacecraft body, but if when we measure the calculate the potential difference between the two tips of the probe, we can cancel out the offset of the probe offset from the natural the plasma potential. Okay, sorry that maybe I must go to the center and finish my talk. And in the last, I wanted a little bit about the future, the magnetic field and the electric field measurement in the future missions. And the one some direction for the future mission is a simultaneous observation at multiple locations. And we made the magnetic field and the electric field measurement by a single spacecraft, but we cannot have the 3D information about the magnetic field and the electric field the 3D information of the magnetic and electric field, and so that we cannot 3D the structure or the configuration of the magnetosphere. So by the multi-location observation, it makes possible to examine the instantaneous spatial gradient. And when we get the gradient information about the gradient of a magnetic field, we can determine the electric current flowing in the magnetosphere, and we can determine the propagation direction of the electromagnetic waves. And so the spatial scale to examine, for example, electric current or the electromagnetic waves is determined by the spatial separation distance between the observation points. And in some cases, these multi-satellite projects are already started. For example, the cluster 2, they have the 4 spacecraft, and the separation is from several hundred to several tens thousand kilometers, and it corresponds to the ion scale as a phenomena. And the second one is the THEMIS. it is the cluster is launched by the European Space Agency, and the second one is the Themis, launched by the United States. And the separation is much shorter. It ranges from 100 kilometers to several thousand kilometers. So the physical target is the magnetospheric configuration and electron scale. It can examine the much shorter the scale of the phenomena. And then now the MMMs is the observing the magnetosphere by the the spacecraft. And the separation is much shorter, 10 kilometers to several hundred kilometers, and it is now examining the electron scale as a phenomenon. And these are the multi-satellite project should be carried with much more the spacecraft, and it such as the project will make more advanced understanding of the magnetosphere. Okay, that is the last slide. Thank you.
Okay, thank you for Professor Matsuoka. I will still have a time for one or two questions. Yeah, Professor Matsuoka, I have a very simple questions because I learned a lot about your effort to reduce the to increase the magnetic cleanness on about the spacecraft. That is very important for magnetic field. Yeah, because of in Taiwan, we always notice that the magnetic cleanness, but the main goal for this magnetic cleanness is for navigation. How about the requirement for the magnetic cleanness for navigation and magnetic field measurement? How different?
Okay. In the space missions, we define the requirement of the magnetic cleanliness. For example, in the case of the MMO, we define the requirement to each instrument to reduce the magnetic field less than 5 nanotesla at the distance, a 1 meter distance from the instrument. But I think that that requirement should be determined depending based on what is the target of the mission. And in the case of the MMO, because MMO, we defined the very strict requirement.
Your signal is losing. Hello?
Hello? Are you hearing?
Hello?
Are you hearing?
Yeah, it's okay.
It's okay? Sorry. Yeah. Okay. That the magnetic cleanliness requirement should be defined based on the final target of that mission. And in the case of MMO, the requirement is, I think that it is a little bit difficult to achieve, because we need to measure the very small magnetic field around the Mercury. But I think that in the case of the navigation, we can navigation around the very low altitude orbit around the Earth. The magnetic field intensity is very rather big, and I think that we can relax the requirement to the spacecraft about the magnetic cleanliness. And then, yeah, of course, we have to define the requirement in number based on the final goal of the final target of the accuracy or the resolution of the magnetic field, we must measure by that mission. And I cannot say the number in detail now, but that requirement should be different depending on the target of the mission, and the requirement should be different depending on how long boom we can use. If we can use the very long boom, for example, we use okay. Oh no. Okay. In the case of the Kaguya, we had the very long boom, 12 meter length boom, and when we can use the very long boom, we can relax the requirement to the about the magnetic cleanliness. But when we cannot use the long boom, very short boom or something, we have to make more strict the magnetic cleanliness control. Is it okay? Is it what you wanted to know?
Yeah, it is very clear. It is very clear. Thank you very much. Okay, so let's thank our speaker, Professor Matsuoka today. So thank you very much.
Thank you very much.
Okay. Yeah, it is great to have your talk. Yeah, so see you. Bye bye.
Bye bye.